It's expected within the next few years, a majority of the country is going to be very competitive for solar plus storage as opposed to gas. Now, wind by itself is already beating gas. And I think that's the true tipping point for hybrids and for pure play renewables, is when it costs less to build a new plant than it does to continue operating our existing assets that we depend on today.
I'm Libby Wayman. I teach the MIT Energy and Climate Ventures course, and I'm also an investor at Breakthrough Energy Ventures and president of the board for the Boston Women's Energy Network.
I'm Danielle Merfeld. I'm the Chief Technology Officer for GE Renewable Energy and a corporate officer of GE.
Welcome, Danielle. You and I had a great discussion for a live event for the Boston Women's Energy Network, and I'm excited to catch up further today. First, tell us a little bit about GE Renewable Energy as a business and what it means to be the CTO.
Sure. So our renewable energy business is a $15 billion enterprise. We consist of an onshore wind and offshore wind business. We make wind blades for the industry. We have a hydro business that's very long and successful. In fact, we have about 25% of the world's hydro installed base and just over 40,000 wind turbines out in the field. And we also have a grid business that's a part of our structure. And our GE Grid business serves about 90% of the world's utilities. So we are a global player in renewable energy.
That's a pretty massive scope and really exciting to be talking technology across that scope of renewables and across the industry. First, can you kind of take us back to how you got into this field and bring us to what you studied in college?
Sure. So I chose electrical engineering, not by any foresight and really understanding of what that meant at the time, but I decided that I thought lasers were cool. There was a lot of opportunity to learn, and I didn't think I was going to have to stick with it if I didn't like it. So I made an easy choice to go into electrical engineering, and I just never looked back. Had a great time learning, a lot in undergrad, and then decided to continue that with graduate school, which is where I really deepened my focus on semiconductor devices specifically. In fact, the area of semiconductor devices that I focused on in particular was called wide bandgap semiconductors, which have a pretty broad range of applications.
And can you tell us a little bit more about wide bandgap semiconductors? What's their scope? What can they impact in the energy sector? And what's their significance to the energy sector?
Sure. So when I first started working with them, I was actually looking at how to use them for sensors and light emitters, because they're great at finding this part of the spectrum that typically was not accessible through solid state devices. So think blue lasers and solid state lighting. But those same semiconductor devices are also really great power electronics. In fact, they're actually way better than the silicon devices that we commonly use for power electronics in almost all of our applications today. They just weren't as cheap, and they weren't as prevalent because they weren't sitting on top of this huge computing industry that uses silicon semiconductors for ICs. But they're actually way better in terms of efficiency, power density, temperature rating. So if you consider that the energy industry is increasingly built on a backbone of power electronics, think inverters and converters and transformers, all the pieces that connect our power generation to power distribution and transformation and all the way to our loads. Power electronics is a key part of that. So if you can improve the efficiency, reduce the cost or the weight, or need less cooling, you can revolutionize the energy industry through power electronics.
And what about this category of semiconductors makes them impactful in those ways to improve the efficiency and reduce the weight and the volume?
Sure. So it's actually right in the name, wide bandgap. So that refers to the band gap of the semiconductor material. And the wider the band gap, that speaks to the energy that it is transferring between bands when it moves charge around. So it takes a lot more energy to move a state charge in a wide band gap semiconductor material, meaning that smaller levels of energy like thermal energy doesn't impact it. You don't have leakage of electrons when you don't want them unless you have very, very high temperatures. Whereas silicon, you will ultimately have more losses in your system just based on natural thermal effects. But you can also pack a lot more current through these because, again, it can handle a lot more power. So you might need a 10th or a 20th of the size chip to move the same amount of electricity that a much larger silicon device would need to be. So that's what drives the scale, the size. A bigger drive on size is actually all the cooling that you typically require to run high power semiconductor equipment or power electronic systems. So not needing cooling, smaller chips is a nice factor, but being able to operate at higher frequencies, which also shrinks all of the other complementary pieces of a power system design, all the inductors and conductors and part of the system. And when you can operate a power electronic systems at very high voltage, you can have low current. You get the same power if you can move those two dials. And when you have low current, you have smaller wires, less copper. So it's just simply a cost flow benefit for moving to higher power, higher frequency, higher temperature ratings. It compounds the value of your system.
Very cool. And my understanding is that you went directly from your PhD to GE Global Research. Was it this work that took you from your PhD to the research center?
Yeah, it actually was. I mean, I really had a hard time deciding what I wanted to do after my PhD, and sky was the limit. I had no preconceived notion of going into industrial R&D, and I frankly didn't know much about what GE was doing in this space when I interviewed there. But I found that this was maybe the one place in the world where I didn't have to choose between all those applications of solid state, wide bandgap semiconductors. I could do sensors, I could do lighting, I could do power electronics, communications. They were doing it all. And they had a lot of interest in pushing the envelope of technology in this space for their various industrial applications. So to me, it was like being a kid in the candy shop.
And so what did you work on there when you first started at the research center?
So I first landed and took on probably the most exciting role I could have had at the time, which was this move to transition from conventional lighting to solid state lighting. So using those wide bandgap semiconductors to fill in the parts of the spectrum that we didn't have in solid state, and transform from the company that was known for creating that lighting enterprise and really going to the source and changing it all. So it was quite exciting.
Yeah, I mean, what a place to revolutionize lighting, right in the home of Thomas Edison. Yeah. Very cool.
Absolutely.
Okay, so where did you go from there within GE?
Well, the best things that have happened to me in my career are sort of nice because I'm positioned with a broad technology background, but there's a lot of luck involved too. So the biggest luck I had was in the opportunity that sprung up after about 6 or 7 years at the research center, working in the semiconductor space, building a team, learning my leadership skills development. And this was an opportunity because we had quite a few DOE programs in the solar space. And they really needed a leader to help coordinate these various programs. And I thought it would be interesting to try something new. I was very interested in solar. And to me, it was not as big of a technical step because the solid state devices that I was working with, you give it energy, it gives you light. These were, you give it light, it gives you energy. So there was a lot of places for me to build on my foundation and add value quickly. And then I just fell in love with it. I mean, solar was magic to me. It could transform our industries, and GE, our energy business was a foundational part and is still a foundational part of the world's energy structures. So again, what better place to try to change the world than the place where your impact can have the most global footprint. So I started in solar. We had a small business that we were launching, and we'd made some good acquisitions. We were developing some thin film technology. It was a wild ride, and it's really been fun. But that kind of got me in this track on energy. And although I've had other roles since then where I took on broader scope around electrification or electric power systems, I really tried to stay aligned with energy throughout it all. And then about 2.5 years ago, I got the opportunity to move from GE's Global Research Center into our renewable business, which is just coming together, just spinning off as its own tier 1 business within GE. And they had never had a CTO. So it was a great time to form that team.
So it sounds like from your description of GE Renewables that the business really encompasses a pretty broad scope across the industry. I'd love to dig in with you about where you see the future of renewable energy, and particularly the technologies that can get some of these exciting but pretty mature energy technologies even to the next level and drive deeper penetration of renewables into the energy sector. So maybe we start with wind, one of GE's major business lines. First, can you just tell us the status of the wind energy sector? Where are we today in terms of its role in the energy sector and the technology?
Yeah, so wind is definitely exciting. It's seen roughly 50% cost reductions in the last decade. So there's a significant growth and opportunity for it to hit the market because it's becoming more and more viable every year. About 40% of the global growth in electrical output last year was based on wind. And this is in context of almost 75% of that global growth is renewables and storage. So wind is a part of a new club that's really taking over the new power generation growth that the world is demanding. The exciting part about wind in the industry, though, is as much as we have great new innovation on the threshold of driving that cost down even more, there is a considerable amount of opportunity today just with the technology that's on the shelf.
And so I think it's interesting that wind represents such a big portion of the market in terms of new energy technology that's being installed, not only as a share of renewables, but as a share of the total sector. And yet it's only about 7% of today's global energy mix. And so now you're talking about the technologies. What are some of the technologies that you're most excited about to drive yet further adoption of wind to grow the percent of total global energy mix that is attributable to wind?
Yeah, Libby, you make a great point about that big differential between how much new power is based on wind and how much of the existing framework is wind. And it is quite a big difference. So much of that is just based on the sheer magnitude of our energy industry and how big our global network is. So it's going to take a lot for wind to penetrate deeply into that base. Although every year that we're retiring more coal, every year that wind's costs come down, it speeds up. So the next big phase of wind becoming even more highly penetrated is all based on cost. So what drives the wind's levelized cost of electricity down further? It's simple. It's decreasing the amount of cost of each turbine and the framework of the system that it sits in, and in increasing the amount of power you get from each turbine. And that is usually referred to as the capacity factor. It's the amount of kilowatt hours generated per rated kilowatt. A lot of ways to do that are fundamentally longer rotors. There's a lot of opportunity in controls to modify and use the turbine differently and essentially let it survive past its load ratings in some cases. So you can really engineer the output in a way that you couldn't have even 10 years ago. Some of the other things that are coming have to do with the components themselves. The big ones are rotors, towers, generators.
And so to put those developments into context, where is wind and where are wind turbines today? We just saw a new product release from GE. Can you tell us about the new product? What's the rating of the turbine? What's the diameter of the rotor? What are the wind speeds that it can work, the cut-in wind speeds and the capacity factor? Just kind of ground us in the state of the art today.
So there are several different segments of how wind plays. So what works in Germany isn't the same turbine that will work the best in the US. So that's probably an important truth for people to realize. The same configuration isn't best everywhere. But something like in Germany, our recent product launch there is our Cypress machine. It's a 5.3 megawatt, 158 meter rotor behemoth, and it actually has a jointed blade. So to be able to make a blade that long and be able to transport it around the countryside and build it in these very constrained environments and ship the parts, we had to do this really novel innovation about separating the blade and building it in two pieces and joining it on the field. That's one important innovation that I think I wanted to highlight in that launch. So we've just announced in our offshore wind business another really large wind turbine system. In fact, the largest one that exists today on the planet. It's a 12 megawatt, 220 meter rotor system. That means each blade is 107 meters long. That's the length of a football field plus both end zones.
Wow.
And it's just incredible. The engineering capacity for this is mind-bending.
And I can't believe that your onshore turbines have jointed blades. So tell us what goes into a structure that large with that much force on it, 100 meters up in the air or more, with a jointed blade. Can you tell us a little bit about the technology that goes into that?
So the structure of that system and the joining of those two pieces is really where the magic is. But I would say in any wind blade, the aerodynamic shape of the blade and how the blade is pitched and controlled is really the core. That's the key. That's where you make the engine of the wind turbine, move. So all that joint, all the magic that we had to do to engineer the solution, that was just gravy on top. That was just to solve a logistics problem. That was just to be able to extend that rotor a little bit more. What we found, however, is that in addition to solving a logistics problem, we've also opened up amazing flexibility, not just in our supply chain, but also in the customization of those tips. And can we think about modifying that tip design? That's where most of your power is captured in the wind, is in that outer, 20, 30% of the blade. And do we start thinking about tips that are designed for certain environments, or even for, in the future, certain pads on a wind farm site? That flexibility that we get with each innovation is sort of like the bonus after you run the hard race, and then you realize that there's more to come.
Yeah, that's definitely a benefit that I hadn't anticipated. And for the offshore machine, that's a giant. That is enormous. Are those segmented blades as well?
No, in fact, luckily for us, they don't have to be, because and typically in the offshore wind industry, you're going to be manufacturing your blade at a port or near a port and then transferring it to the field, essentially the place where you're going to be developing your turbines, on water. So it's flat. You don't have to go under bridges or over mountains or under tunnels. It's a lot easier of a logistics issue. But that doesn't mean in the future we wouldn't see so many benefits from a jointed design that we wouldn't want to do that. But right now we don't have that in our design.
And I don't know if you can talk about this, but can you give us a peek at what might be coming in terms of technical innovation that could take wind to the next step?
Yeah, one thing that is easy to overlook when you think about a big system like a wind turbine, because you think so easily of the physical manifestation, like we were just discussing, the blade or, the design of any part of it, is the digital side. So being able to, just like you do with your phone or just like a Tesla does, being able to update the software or the controls on an asset and improve its performance over time, developing apps that change how it engages with its environment, or using it to operate the system in a way that extends life or performance. We're at the very beginning in this industry of being able to operate our systems that way, or even having the digital engagement on a services side to do that. So I think there's a tremendous amount of opportunity there. But in the meantime, we have a lot of physical stuff too. One thing I didn't mention when I was talking about jointed blades is additive technology. And those of you who are very familiar with additive printing or 3D printing of parts probably think of metal parts. And our GE Aviation business has been pioneering making highly specific, dense metal alloys into parts that go in hot parts of the jet engine. So we get this space in our DNA in GE. What we need in the wind industry and in renewables overall is a whole different approach to additive technology. It's not about a high cost, high dense, high temperature metal alloy part. It's about really cheap, big, stable components, whether it's the blade or the tower. We're talking about revolutionizing not a detailed component that requires a lot of care for the design. We're talking about how do you make something more robust, higher quality, more modular, more on-site. We just announced a great partnership to continue to develop our additive printing work on towers. And now think about this. If you can print the concrete and the structural integrity of a tower, now you're not limited to the foundation or the pedestal width or diameter. You can start to change the heights of your designs without having to go through a whole redesign of the tower structure itself. It gives you a lot more flexibility, customization. It opens up viability on scale and size that we just don't have with a conventional steel tube design. So again, early stages, but additive is transforming just about every part of our renewable business. And I do mean hydro and grid and wind. And it's just, it's a ripe field.
It does seem like an unexpected application of additive, just the large format that would be required for wind and other technologies. I'd love to switch over to hydro. It sounds like you have a really large portion of the installed base. Can you talk a little bit about the state of the art of hydro? It's certainly a technology that's been with us in the energy sector for many, many years, decades, centuries, and would love to understand what you're seeing in that field. Is that a robust growth sector, or is it facing some challenges as the most mature sector of the energy industry?
Great question, Libby, because there is a lot of discussion about hydro, given that it's partnered with these other renewables that are growing like wildfire. I mean, solar and wind are leaving hydro in the dust when it comes to growth rates. However, hydro is still almost double the total combined power generation capability of the other renewables. So hydro is experiencing not a growth of new hydro in most regions of the world, but a renaissance in opportunities for refurbishing. So when you go through a huge cycle of environmental review to build a hydroelectric facility, it's a lot cheaper and more efficient from a societal use of capital to improve that performance over time, rather than to find another river somewhere else or another dam opportunity to create a hydro solution. The second thing, so refurbishment will grow and is taking on new life here in the US as well. But the other opportunity is using hydro in a way that supports the grid because of renewable integration and growth and penetration. And that is the pumped storage aspect of hydro. So in addition to being a generator, it can also be a storage device. And it can instantaneously provide feedback to the grid. And that's something that I don't think much of the market that hydro plays in rewards it for today. We could have a whole other podcast discussion about the electricity markets and how they're likely to evolve because of renewable penetration. Hydro is a big part of that, and we can talk in depth about that too. I think there will be more value created in hydro, and there'll be more opportunity for us to take advantage of that storage capability going forward.
Yeah, it does seem like the resource can provide some grid services and, like you said, storage as well to integrate with renewables. One area that we've been looking at Breakthrough Energy Ventures has been distributed low head hydro. And we think that there could be some new technologies that can actually open up that resource for new development where, as you say, the large hydro resources have a lot of challenges when it comes to new deployments.
Mm-hmm.
And so in terms of refurbishment, what are some of the things that are impacting refurbishments? Is it just kind of a maintenance schedule? Are there new requirements that hydro facilities are required to meet?
I think that the age of many hydro facilities around the world is the key driver. Just, the infrastructure ages. If you are 60 or 70 years past the implementation date of that system, it's likely going to need not necessarily overhaul, because I think repair, you can stretch these things for a long time and you can replace components and repair your system and continue to allow it to operate. But if you're only accessing 5 or 10% of the total available opportunity because you're using 60 or 70-year-old equipment, then it becomes really interesting. You can change out your main generation equipment and really upgrade to the more modern hydroelectronic, hydro flow or hydro designs, but also create a digital component. I mentioned already is, can you implement new strategies for operating a hydro plant in addition to upgrading its physical equipment that create more value for the operator? That's another key part of upgrading hydro, is not just the turbines themselves, but the digital interface.
And what would that digital interface need to take into account to optimize its operation and interplay with the grid and other demands on the grid or other renewables?
Well, all of our digital engagement with electrical systems or energy systems probably needs two parts. It needs to have an edge component where it can make decisions at the site. It doesn't need to be able to connect to the mothership or some cloud capability somewhere. It can actually read the conditions of the system and change its operation to extract the most value. That means it has to run very complex in some cases, but sophisticated algorithms to do that calculation of what's the most optimum next step in a closed loop, real-time controls loop. The second piece beyond that edge capability is accessing global information, typically through cloud connectivity, of electricity rates, demand from the grid, forecasted need, all the things that are less on operation at the site and more on performance and operation of the business. So how can this plant play into an economic approach or a market at the most optimum level? And so you put those two together, and that's the sort of the digital story, is how do you operate more effectively on one hand, and how do you use it most effectively in the market on the other hand?
Mm-hmm. And I guess expanding from hydro in its form of storage, I understand you guys also have a lot of work going on in what you call hybrid energy and incorporating storage and focusing on utility storage. Can you describe your activities there?
Sure. Our hybrid business is our newest business within our renewable energy family, and it's one of the most exciting. It's easy to simplify it and say, oh, we're just sticking batteries with other systems. We put batteries with solar. We put batteries with wind. But we also put wind and solar together. I mean, there's a whole combination of renewable energy assets and energy storage that it's easy to imagine you're just assembling, but in truth, it's actually more than the sum of the parts if you do it right. And by that, I mean, if you're using an energy storage aspect, a battery, and you're taking advantage of the cost of that coming down over time, implementing the really low cost of a renewable energy platform like wind or solar, you're actually able to play on the grid in a way in our markets today that's looks more like a gas turbine facility or a steam or a coal plant. I mean, these are revolutionizing sort of the dispatchability and flexibility of a typical renewable only site. So the value creation is quite a different calculus for a hybrid system than it is for a just plain wind or just solar system. One other aspect I just want to mention, though, is as renewables start to penetrate more and more, the grid will become more dependent on features that help it reliably operate or provide some ancillary benefit. And the controls that the hybrid plant is operating are also going to help the grid. It'll be able to interface and read the grid's needs and demands and articulate the response from this collection of assets, batteries and wind or solar, in a way that we just can't do today. All of that choreography happens on the grid side today. And if it can be done more at the plant level, you take cost and complexity out of the grid side.
And how do you think about hybrid renewable energy systems and the value that they bring to the grid? Do you think about it in a capacity factor? Like they have a capacity factor that matches a gas plant? Do you think about it as availability or dispatchability? And where is that today for hybrid plants and at what cost?
So you mentioned capacity factor. That is the main driver for typically wind plus solar hybrid solutions. And their big markets for that right now are in India, in the US has some growing. The driver there is if you're going to build a new substation, a distribution unit, and you have a big renewables plant out in the middle of nowhere, you really don't want to build all that transmission if it's only going to be on when the sun is shining or if it's only going to work when the wind is blowing. So adding the cost of the batteries to that is marginal with respect to the cost of that transmission line. So the capacity factor of that plant is a really big driver for the overall cost payback of that entire investment. So capacity factor is a big deal. And we can get up to 60% capacity factor in some cases by just combining solar and wind.
And how does that asset compete with, for example, a natural gas asset that might be the alternative at kind of the grid level? I think it makes sense that installing batteries and hybridizing a plant is a great alternative to building out transmission line, but at a click higher level, the system has the option of installing a hybrid plant versus a natural gas plant. Are those two at parity yet, or is there still a way to go on the hybrid renewables side?
They are at parity in many parts of the world. In fact, I would say we've seen areas where it's already cheaper to do that with, say, solar and storage than a gas plant. And of course, it's highly dependent on gas price and location. But if you think about a typical large gas turbine facility, those turbines run, the big ones, the good ones, ours, frankly, from GE, are running in the low 60%, low to mid, maybe 65% capacity factor is a really great efficiency level. So if you have that and you have very cheap gas, you're competitive. But when you start to see 60% or plus hybrid solution coming out, or you can add storage to that and improve it even more, so over 75% capacity factor, say, then you really do have a shift in the balance of opportunity.
And do you think that the price of batteries and the cost of batteries are where they need to be for new build solar and storage or solar storage and wind plants to continue to displace natural gas plants, as you know we've already seen displacements in coal, or do we need further cost reductions in storage to make that truly competitive at a larger scale?
So great question, because we're at the tipping point now. There are parts of the Southwest where we're seeing solar plus storage beat fossil-based plants hands down in terms of overall cost. but most of the country isn't there yet. We expect that with the expected cost of batteries declining as fast as they are, and the learning curve is very predictable, and we've seen it in wind and we've seen it in solar, so we get how to project this, although we almost always under project that cost reduction. It's expected within the next few years, a majority of the country is going to be very competitive for solar plus storage as opposed to gas. Now, wind by itself is already beating gas. It has been for a couple of years on just pure cost if you're going to build new gas versus build new wind. In the next few years, we'll start competing on variable cost. And I think that's the true tipping point for hybrids and for pure play renewables, is when it costs less to build a new plant than it does to continue operating our existing assets that we depend on today.
Absolutely. And you also have a grid business. Transmission is notoriously difficult and impossible almost to build. Are there innovations that can break down some of those barriers for new transmission to be built to connect parts of the country and even internationally that have great renewable assets with those that don't?
Yeah, the biggest growth area in transmission is HVDC. And it's a hot area partly because it's becoming more cost competitive as innovation happens and we bring the cost down of these very complex systems. But also in the HVDC space, we're seeing it come into play for, say, offshore wind, where you need something like HVDC because you can't transport that much power through this medium, water, without having too much losses. So AC transmission doesn't work. So HVDC is starting to grow partly because offshore wind is demanding it, and that volume is reducing costs faster for on land applications. And the reason why somebody might want to use HVDC on land, besides long haul, going from the center of the country to the coast, where the efficiency is much better, you don't have as much transmission loss, you also need HVDC just to connect parts of the grid that are at different frequencies. We see this in Europe, these base stations that are connecting a 50 hertz and a 60 hertz grid. So if you fast forward and you think about how the world adopts more renewables, some of the solution is actually just connecting the transmission lines we already have and being able to share when it's sunny or windy in this part of the world with where it's not in this other part of the world. And you've taken out the need for storage or gas or fossil-based support because you're able to instantaneously move wind energy hundreds of thousands of miles across this whole network. So those links are going to be really important. And that's also a big part of the innovation in transmission.
Mm-hmm. There's a huge component of opposition to high voltage DC transmission just because people don't really want it around. How do you combat or how do you address that challenge to get projects built?
Well, first of all, I think the most important thing we can do for our communities and our policymakers is just provide information. So some of this is just the basics of what is it really and what's the boogeyman risk, what's not real, but you have fear of. The good thing about HVDC is it's a lot smaller footprint than AC conventional lines. So if you were to use the same corridors, you could get multiples of power flow through the same corridor just by switching from AC to DC in the lines. So that's one benefit that even people who are NIMBY and don't want to see new lines would be happy for, because you're using the space that you've already created for power lines. You're just upgrading the ability to hold capacity there. Now that's costly. Ripping out things that work to put in things that also work doesn't always happen and isn't always supported by policy. But I think the main question that we're going to have to come to grips with to decide how we move forward in this space is it worth it? If it means we add transmission lines over a mountaintop or in an area that's got population that can see it, is that population going to be healthier, happier, safer, wealthier because of it? And do they understand that? Do they believe it? I think the data, we just need to provide the data so that we can make good societal choices.
And as a product company, what role do you normally take in that kind of communication and stakeholder engagement? Or do you just support your partners who take on the project development and just kind of provide that data and support them in that kind of communication?
Yeah, we do as much as we can in terms of highlighting the opportunity, talking about the benefits. Generally, we don't lobby in communities. We try. That's definitely our customer view, is that they're the owners of these equipment that we sell. We're the OEM, so they're going to own this equipment and operate it for the next 50 plus years. So that's their message to drive, but we try to equip them with everything we can. When we're asked to speak on panels or provide expert opinion or, insights, we definitely rise to that and try to help in every way we can, because it's good for all of us. Most of the people that I work with, most of the people that are in our company are there because they want to improve our lives and improve the planet. So it's our mission.
So switching topics a little bit to a sector that you've had as a company a role in over the years, but are a little less involved today, which is solar. You're certainly still kind of engaged in the sector. I would just love your perspective on where solar technology is today, and if it is basically completely mature or if there are yet big steps ahead for technology advancement and cost reduction beyond where it is today.
Yeah, so solar is so exciting. And I mentioned earlier the amount of cost reductions in wind. Solar is even more impressive. Over 90% reduction in the cost of solar in the last 10 years. So tremendous improvement. The good news is it's going to continue to improve, partly because of technology advances and partly because continuing scale. And when you talk about solar, many people think of the solar modules or even the solar cells that make up those modules. And that's an important part. It used to be 70% of the cost of a solar system. Now it's probably closer to 30%. So the cost of those solar panels coming down is really going to help drive the overall solar cost down, but not to the same degree it did when it was the majority of the cost. That being said, the technology of typically silicon-based solar cells is improving. There's a pretty general type of solar cell that's manufactured in mass, mostly in China. That's kind of upgrading. We're seeing new improvements going to N-type solar or PV. And I think we're going to continue to see that. Multi-layers, where you're extracting more of the wavelengths of light from the sun. But let's not count out thin film. Even though it's a very small minority of the solar panel kind of opportunity, it is highly efficient. It's growing fast. There's lots of opportunity. A lot of different types of compounds can be used. And frankly, it's a lower CapEx, lower environmental impact approach. So in addition to trying to make clean energy, we also across this industry are thinking about the circularity of our products. How much recycled material are we using in them? How much recyclable material are we using? And how do we close that loop and reduce our costs of materials, but also reduce the end of life costs and any kind of mitigation? It's still a great payback on the carbon or on the materials that's used. Way better than almost any other kind of energy generation. Wind and solar kind of lead the pack, but they can get better. So solar will continue to move in that direction of getting better in cost at the module level. And one thing I would say is don't discount the piece that connects the solar to the grid. I mean, it's formed specifically through the solar inverter. That's where you're going to have the controls that not only make sure that your solar field is operating well, but that you're transforming that energy so that it can operate and connect to the grid in a way that enhances the grid stability and doesn't put it at risk. One term you'll probably hear is grid forming rather than grid following. And the power electronics that we've used historically in wind and solar is grid following. It is based on semiconductors. These typically fall into a category where the voltage at the grid is set by these big gas plants and steam plants and conventional thermal facilities. And that's changing. So we're now able to design power electronic systems or solar inverters, for example, that set the voltage at the grid and keep the grid healthy and prop up the voltage far, far away from any kind of large central fossil plant. And that changes the ability for us to add more renewables to the grid.
So such an awesome scope that GE covers, particularly in the renewable field. So I just love your perspective. What do we need from a technology perspective to get to 100% renewables? Can we get there? And what technologies are going to take us there?
Well, the good news, and it's maybe not what you expect to hear, but the good news is we can get almost all the way there now. Like there's a great report that summarizes a lot of what I'm going to say that just came out a few weeks ago called 2035 Report. And you can find it at 2035report.com. It's a policy paper out of Berkeley. I highly recommend it. But in that, they outline things that our own internal modeling has also shown us in GE, which is the grid can handle up to 90% of additional renewables. I mean, we can shift from where we are today, which is around 16% hydro plus another 9% wind, solar storage. we can go up to 90% within 15 years. So by 2035, and it's going to cost less than our energy does today because of these cost curves that we've been talking about. It'll create more jobs, be safer, a lot less carbon. And, according to that policy paper, it can be done pretty effectively. And the need to balance that, the other 10%, is gas turbine facilities we have today that we just keep online and don't operate as much. They're the balancing part. So your question was about getting to 100%, and I didn't answer that yet. Getting from 90 to 100% is going to be the hard part. And it can be done at a certain cost. And I think our challenge is, I would say, let's not worry about that cost yet. Let's spend the next 10 or 15 years getting to that 90% and having that scale and that innovation and that experience drive whatever novel innovation comes next, because then that last 10% will be more prepared to struggle with. If we try to get all of our ideas battened down now, we might never get off the starting line. We might, if our goal is 0% carbon in our energy systems by 2050, what happens in 2040 and we're not there yet or halfway there yet? So I love the idea of giving ourselves earlier, more aggressive goals. And at the end of the day, we're going to find a way to close that gap to 100%. We have to.
And for the technologists out there, what are some of the big technical challenges that they can sink their teeth into, either to take the wind or solar or hydro sectors to just their next level, or to close that gap between 90 and 100% renewables?
So I think it's going to continue to be the same categories of work we're working in today. It'll be new materials, lighter weight, stronger, stiffer, capabilities of materials, controls and digital management. And it'll also be new ways of connecting quickly. There's so much innovation to be had in designing the grid. Utilities spend a lot of time and money researching where to put the next plant and permitting that. So I'm working on one end of the spectrum where we're making the equipment and selling it to a user who's going to install it with us and operate it. There's still a whole bunch of work to be done to make sure that we put these in the right places where they can be the most useful to the broadest sector of the population. There will be differences in how we run our energy markets and how we trade. Today, we have a very centralized method of making energy and selling energy to the population. What if anybody could make and sell energy? How does that change the dynamics of growth and who engages? So there's just as much innovation on business models and policy to drive the right behaviors and to reward the things that are most valuable to our grid or to our society. So innovation is just, I could list this forever. It's exciting. There's things we cannot even imagine today that we'll be using in the next 10 years. And in the current 10 years, we've got a lot we can do.
And as you are trying to identify those areas of innovation for the business and for bringing new talent into the organization and for just kind of seeing around corners of the industry, how do you stay abreast of some of these innovations and totally new ideas that may be orthogonal to how people think about it today?
Well, so I'm lucky in that I'm still connected to our secret weapon in GE, which is our GE Global Research Center. So our research center is connecting us to ideas around how to use artificial intelligence and blockchain. And I could name a bunch of buzzwords too, because in some cases, they don't mean anything to me until I can use them in our products. But having a group that is working on that next frontier, even if it doesn't matter to me yet, means as soon as we can link it to something I need, I can access some manner of expertise there. Beyond that nature that's very unique to GE, having this industrial research lab, we also are learning a tremendous amount from the government agencies that we work with, the national labs. NREL has a fantastic number of really talented scientists and technologists that work there, and universities around the world that we engage in with, or we do internships just to kind of get into these places and understand some of the innovation happening there. So there is a lot of people that I would love to talk to, and I get to scratch the surface of that pool of talent, and going to conferences and doing virtual meetups is a way for me to stay connected with that. There's so much to catch up on.
And as a technical leader in one of the tier one businesses, you mentioned that technologies aren't really real until you can put them into a product. You started off your career and spent the bulk of your career so far as a technologist in the Global Research Center and then as a technology leader there. How has your thinking changed or your leadership style evolved from kind of a research organization to a business or in other ways throughout your career trajectory?
Yeah, the biggest difference in the environment that I worked in at the research center versus in the renewable energy business or any of the GE businesses, frankly, is the urgency and speed of which our teams operate. Certainly the research center was not slow, but we were working on such longer cycles of innovation and demonstration that, a day was a week, no difference. A day versus a week is an infinite difference in the renewable space. So having things that we're launching new products every year means every week matters and every miss is painful. We can't have the delays that maybe you could absorb in the research world a little easier. My style has probably flexed maybe more than I realize in terms of doing a lot more listening, having humility when it comes to new spaces. And wind, I was not a wind, and I still am not a wind expert, and I'm surrounded by wind expertise in this business. So knowing that I get to help chart the path of our strategy, but I'm leaning on people who have spent their careers doing this and understanding in depth the technology opportunity or the risks. It's given me an approach that at the research center, I didn't need as much, and I need it greatly in this space.
Well, I'd say it would be a pretty big display of humility for CTO of the business to say you're not a wind expert. It's probably all pretty relative. That's been an amazing look across all the different sectors of renewable energy. So, Danielle, what's next?
I think the way we want to think about renewable energy and its penetration in the grid and its transformation of our energy sector is really important. We talk a lot about the connection of renewables to the climate crisis and to reducing our carbon footprint and ultimately leading to a zero carbon energy sector by 2050. That's a baseline that most everyone agrees on. What I think we should focus on is, in fact, our energy sector should be decarbonizing much faster. We need to be at a faster pace because the other sectors that also have carbon footprints that need to decarbonize are going, like agriculture, buildings, transportation. They're going to depend on the energy sector, giving them green electrons so that they can decarbonize. So if we wait until the finish line to provide that in our sector, we've really delayed those other sectors from their decarbonization plans. So we talk about the global crisis, we talk about our carbon plans and the sustainability path we're on. I just would leave everyone with, if you're in the energy sector, you need to be first. We need to be there providing a platform for the rest of the world to do this important work. And I think we can get there.
Amazing vision and amazing charter. Danielle, thanks so much for speaking with us today. I really enjoyed it.
Thank you so much, Libby. I did too.